SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the module 2 for the MOOCs course Power Plant System Engineering. The title of this module is Vapor Power Systems Part 2. In our previous lecture, that is lecture number 9, we have initiated the discussions on the nozzles and its basic theory. So, on this ground we have given the theoretical aspects of nozzle shapes. So, we will revisit those concepts again here in this lecture. Then moving ahead, we have other topics like how do you calculate the mass flow rate of the nozzles, and there is a concept where we call this the nozzle to be choked. So, we will find out under what conditions nozzle is going to be choked. Then we will talk about some discussions about the pressure ratio or what is the importance of pressure difference across the nozzle for desired flow situations. Then we will discuss about nozzle performance parameters. So, till this point of time nozzles are very generic in nature. So, which means that nozzles can be designed for gas which may be perfect gas, or it can be in liquids or water or any incompressible fluid, or it can be a steam nozzles. So, steam nozzles falls in the area that when we have liquid vapor mixture as well. Now, under what circumstances, what different thermodynamic parameters which are going to be governed, so that we can apply the basic theory of nozzles to particularly while handling the steams. In fact, moving further, steam nozzles normally encounter vapor and liquid simultaneously. So, there is a concept called super saturations, which is a very common phenomena that occurs in steam nozzles, and this super saturation is nothing but a irreversible phenomena. We will discuss this its aspects, how this super saturation phenomena takes place in steam nozzles. Now, let us revisit to our previous discussions where we discussed about the nozzle shapes. So, in our previous discussions we derived from these thermodynamic equations about how the flow through nozzles happens. So, based on that we find out for any given nozzles for which the area changes with in a particular directions, we can find out the flow velocity by knowing the enthalpy conditions at the inlet. Then we have the fundamental equations, that is mass flow rate, that is which falls as m dot is equal to rho or A into C by V, which stands for specific volumes. So, we will arrive at a expressions which we call as area per unit mass flow, that is A by m dot is equal to V stands for specific volume divided by square root of twice H1 minus H plus C1 square. Now, in most of the situations while talking about the nozzles, we normally neglect the inlet velocity, because this inlet conditions comes from a reservoir for which this velocities or flow velocity can be negligible as compared to the velocity at any other cross sections in the nozzles. And this fundamental diagram that comes out, that means if you look at a nozzle shape which is initially convergent then divergent, and typically we call this as a convergent divergence nozzles. And if you see this, if you try to correlate this particular figure with respect to this graph and you try to frame or try to understand, what you are going to see is that if you take the any section 1 and section 2 of the nozzles where the pressure stands as P1 and which is at section 1, and we will try to see what is the variation of the pressure, how the pressure changes with different shape. So, we will see that if your direction of the flow is from left to right, which means that in this left to right your area changes, your velocity changes, and also specific volume changes. One interesting thing, you know that both velocity, since flow is going to expand, so of course velocity will be higher changing, and but if you look at the specific volume graph, you will see that in the initially the change in the specific volume is less, but however when you go along this length, we will find that specific volume also change in the specific or slope of the line of specific volume is progressively higher as compared to the changes that happens with respect to velocity. So, this gives some important information that the dominance of specific volume at a later stage is higher as compared to the velocity. And based on the, we will find that the area curve will have a minima, which is the minimum area at this point, and this minimum area refers to the, for a particular nozzle is referred as a throat. Throat means this is the minimum dimension what we come across. So, the nozzle for which the area varies across its length is known as convergent divergence nozzles, and the section of minimum area is called as throat. In most of the applications, there are two types of nozzles that we normally come across. One is mainly convergent. So, when you say convergent nozzles, it is mostly used for incompressible fluids or mainly liquids. Now, when you deal with the gas, it is normally preferred to have a convergent divergent nozzles. Now, let us understand what is the basic difference between these two is that when you deal with the convergent divergent nozzle, only convergent nozzles, we will see that your outlet is area is always less than the inlet area, which means that minimum area is always encountered at the outlet itself. Whereas, if you look at a convergent divergent nozzles, which sees that in most of the cases what happens, the initial portion, that means to make this C1 to be 0, this initial area was made larger and suddenly it is brought to this minimum area, which means that, so that this assumption of taking C1 close to 0 holds good. That means, the flow is at the initial state is almost stagnant or velocity is very negligible as compared to any the flow velocity at any other cross sections. Now, considering this fact that all convergent and divergent nozzles are designed and for which in the initial portions we have the shape of this geometry, it is from larger area to the minimum area, and rest of the expansion takes place in the diverging portions, which normally is regulated by the pressure ratio between this throat and this outlet conditions. We will come back to this point later. In fact, in our previous discussions, we also defined parameters like critical velocity, critical pressure, critical temperature expressions. So, it means that those conditions are for a perfect gas, we can find the ratio Pc by P1, that is critical pressure, which is normally occurs at the minimum area or throat, minimum area for a convergent nozzle or at the throat conditions. So, based on that, by looking, and it has also been shown that the critical velocity of the throat is nothing but the sonic velocity. So, these are the some of the important aspects that how these nozzle shapes are decided. Then we will move on to next important topics, that for a given nozzle how do you find out the mass flow rate, and based on this mass flow rate we will say that whether the flow is choked or not. Choking is a phenomena which says that what is the maximum mass flow rate that a nozzle can handle, or in other words what is the maximum or the velocity that we can achieve. So, for that, for this case let us try to understand the first case. Only when you are looking at a convergent nozzles, what happens is that we have some inlet state and we have the exit state. So, initial pressure is P1, that means nozzle is operating between two thermodynamic states, one is P1, other is the pressure what we call as back pressure. Back pressure is the word that we normally use, that when the flow expands to a particular space, the pressure of that space is known as the back pressure. Of course, that back pressure can be regulated the way we want. So, by controlling this back pressure we can actually define what velocity we can achieve in this flow, or what will be the exit velocity at the minimum area in a convergent nozzles. Now, let us understand that when your initial state beginning at this beginning, when the flow does not occur, which means that your P1 and PB they are equal. Now, let us see that if under what conditions the flows will initiate in the nozzles. So, for that reason we have to reduce this PB, so that some flow will occur within this converging space. So, if you keep on reducing this PB, we will arrive at a particular conditions, that is when PB is equal to PC, that is the velocity at the exit of the nozzle will be sonic. So, at that point, that means if you keep on reducing PB to a value which is at PC, which means that the exit of the velocity, the flow velocity will be sonic. So, further reduction of back pressure, it means that further reduction of back pressure will not change the mass flow rate, and for that exit conditions or exit velocity, we know this exit velocity, we know the exit area. So, that way we can find out the what is the mass flow rate at the exit, and that state when the flow is sonic, the mass flow rate will be maximum. But what will happen if any further reduction in the back pressures, means the mass flow rate will not change, and but the gas will expand very violently at the exit of the nozzles. So, whatever expansion that nozzle is going to give, it has given, but the rest of the things, that the subsequent expansion from PC to PB happens at the exit of the nozzles. Now, let us see that when you have this maximum mass flow rate in the nozzle, it happens when you have this critical pressure ratio. Critical pressure ratio is nothing but the pressure PC divided by P1. P1 is the inlet conditions of the nozzles, and that for that we have expressions like critical pressure ratio, critical temperature ratio, critical velocity at the throat, that we derived in our previous lecture. And now, under these conditions, once you have this critical velocity at the throat, then we can find out the mass flow rate based on the information of critical velocity and minimum area of this throat. Okay. Now, let us understand more details of the practical utility how these nozzles are normally operated. In fact, when you design this nozzle, we have two conditions. One is through this area informations, because the minimum area will give you the choke conditions. Now, this at the same time other parameter that regulates the flow is the pressure ratio or pressure difference across this nozzle. So, side by side the true simultaneous effect of area change plus and the pressure difference will talk about what velocity we are going to achieve and what is the physical behavior or nature of the flow in the nozzles. So, based on that we will discuss about two important concepts. One is called as under expansion in the nozzles, other is the over expansion in the nozzles. So, previously we have shown that at the minimum area and you will get the sonic conditions, and that is nothing but the critical conditions. At that critical conditions, the flow is choked, and as long as that critical pressure ratio is maintained. But not necessarily that always we will have choking in the nozzles, because the back pressure is the main culprit, because that normally talks about whether the flow will be choked or it will have some other effect. So, let us understand that in a convergent nozzles what happens, that means how do you talk about the design pressure ratio. So, design pressure ratio is normally encountered by the pressure ratio at the inlet conditions to the minimum area conditions. Now, when we have this minimum area means, that means that is nothing but for that convergent nozzle, that minimum area will be interpreted as the throat. Of course, there is no diverging portions, but since it is a minimum area, it will be throat. Now, if the pressure differences are adequate, then flow will be choked for that pressure difference. So, there are two types of nozzles, one is under expanded nozzles, other is over expanded nozzles. Then what does this mean? So, let us see that when we have a choke conditions, that means we have a back pressure PB, there are two pressures, one is the inlet pressure, other is the back pressure, third is I am interpreting as exit pressure. So, here let us say it is at PC, that means at the we will achieve these sonic conditions at the exit. So, when we say PB is equal to PC, that means the flow expands. So, the pressure drops up to till this exit point. So, at this point we can say it is the PB since the back pressure is maintained at the exit condition of the nozzle, that means that is the design condition of the nozzle, then we say that flow is choked and it will follow this graph, that means pressure will drop along this length of the nozzles till it reaches to PC. Now, let us see that if your exit condition is not at PB, either it can be greater than PB, can be greater than PC, or PB can be less than PC. So, when PB is less than PC, we will call this as a under expanded nozzle, which means that flow has already expanded to this point 2, but beyond that flow also sees that there is again the pressure is below the exit pressure, which means that when the flow goes out, it also sees it further expands outside the nozzles, and this expansion occurs in an irreversible manner. So, this although from 1 to 2 process is reversible, but beyond this it is an irreversible manner, and system brings, that means after coming out it expands violently outside the nozzles till it reaches the back pressure. And how it happens? It happens in an irreversible manner depending on till the flow achieves the back pressure conditions. But in case the back pressure of the nozzle is above the design value, so that means PC we call this as a design value, and if other case if the back pressure of the nozzle is above the design value, then it is said to be an over expanded nozzle. So, here the exit pressure is greater than the critical pressures. So, when it happens, its net effect is to reduce the mass flow rate through the nozzles, and this particular over expansion stops is more relevant when you go for the convergent divergent nozzle. So, let us see what happens in a convergent divergent nozzles. So, in a convergent divergent nozzles, we have already said that the shape of the nozzle is designed such a way that with a certain this very smaller length will achieve the throat, that is minimum area, that means flow initially from at inlet condition P1, suddenly area changes to the minimum area, then the divergence portion happens. So, whatever expansion mostly takes in this diverging portion only. So, let us here in addition to this here since the minimum area occurs at the throat, your critical condition will be achieved at PC, that is PC or TC or CC, which is achieved the throat condition. But to have this to put means that exit conditions is now governed to this throat condition, that means we can get information at the exit condition 2. So, that is what we interpret this PR as the exit condition right now for a convergent divergent nozzles. Now, once you know the information of throat, we can get back the information of the exit conditions. So, we have one more information, that is exit pressure PR, which is normally called as design pressure, and side by side we have also this back pressures. So, here the possibilities could be like this, that your PB can be greater than PR, PB can be less than PR. So, same concept, whether the flow is an over expanding nozzle or under expanding nozzles, and other possibilities could be that the mass flow rate is very small, and so that the pressure at the throat of the nozzle is well above the critical pressures. That means, at the throat we will not achieve critical pressure, because mass flow rate is very small, and then this nozzle behaves in a manner which we commonly use in the incompressible flow, that is known as venturimeter. But venturimeter is not used although the shape is similar to a convergent divergent nozzles, but it does not operate for expansion purposes. So, the concept of venturimeter is not in this part of our course. What we look at right now is that we will try to see that when the pressure difference is more, which means that P back pressure is further lowered. So, then we will have these conditions, that means this pressure at the throat, I mean back, by controlling the back pressures, we can design the shape of this graph such a way that till we reach, that means if we have critical pressure at the throat, then we will achieve the design pressure ratio condition R at the exit. So, this curve stands as 1 till critical pressure we achieved as this PR is achieved here. Now, if this pressure and beyond this, what happens, the definition of nozzle takes place, whether it is will be an under expanded nozzle or over expanded nozzles. So, when we have over expanding nozzle, PB will be greater than PR, and when we have under expanding nozzle, PB will be less than PR. And in between the flow expansion can take place, in between if at some intermediate pressures, if the throat condition is achieved, then the flow will try to expand in the diverging portions, but again there will be recompressions, because adequate back pressure is not maintained. Okay. Now, next we will move to the nozzle performance indicators. We have come across these terms previously while dealing with the turbines, steam turbines, but for the sake of continuity, let me repeat these parameters again. So, 3 important parameters are considered for the nozzle design. One is nozzle efficiency, which is defined as the ratio of actual enthalpy drop to the isentropic enthalpy drop between same pressures. Second parameter is velocity coefficient, which is defined as the ratio of actual exit velocity to the exit velocity when the flow is isentropic between same pressures. And third one is ratio coefficient of discharge, which is defined as the ratio of actual mass flow rate of the nozzle to the mass flow rate which would be passed if the flow is isentropic. So, based on our definitions, mathematical expressions are given here, that is, if referring to this particular figure, there are 2 cases. One is when you are dealing with vapor, which means that particularly when the steam nozzles, when the flow expands, initially it is at superheated vapor, and after expansion it falls to the dome of liquid vapor mixtures. So, the process can take place, isentropic process can take place from 1 to 2s or 1 to 2. But when you deal with the perfect gas, there is no dome. So, rather between 2 pressure differences, we can say that how this expansion takes place from in an isentropic manner from 1 to 2s, and in an irreversible manner from 1 to 2. So, once we know all these informations and we can recall our definitions to calculate nozzle efficiency eta n, then we have velocity coefficient Kb and coefficient of discharge Cd. Now, moving further, we have already emphasized that when you actually deal with the nozzles, normally what type of fluid that we are going to handle. Typically, the fluid that can be a gas or perfect gas or air, Other category could be, it can be a vapor, particularly when it expands, water vapors or steam, superheated steam when it expands in the turbines, and the shape of this passage of the turbines are nothing but a particular fashion, for which we say that they are called as curved axis steam nozzle. So, what it means to us for the nozzle calculations, basically they are nothing but a convergent divergent nozzles. So, here I have shown two particular pictures. One is a simple one dimensional convergent divergent nozzles, typically we call this as a quasi one dimensional flow, which means that only area changes across x. So, for that, in the initial part, as I mentioned, it starts from a big area and normally and suddenly it converges to the minimum area, which is the throat, and then we design this diverging portions based on the area which is available at the throat. Now, normally when you use these nozzles for perfect gas, the divergence angle, which is referred as this theta, this divergence angle is always kept below 20 degree. So, that is that it has, because if it is more, then there will be a breakaway of the fluid from the duct wall and it increases the friction losses. The other part of the nozzle is the diverging portion, in which the velocity increases or flow accelerates, and whatever losses that is supposed to happen, that will happen in the diverging portions only. So, this is what we do, what we say is the circular cross section of a nozzles, which is used mainly for perfect gas and that to generate the thrust. But when you use this particular things in a steam nozzles, because our main purpose is to expand the flow, not to give thrust, but rather to give power. So, for that reasons we call them as a curved axis steam nozzles. So, normally or in our turbine viewpoint, we say that the blades are designed in, curved blades are designed in such a way that flow is aligned in a particular fashions, and this shape of the nozzle is such that we can have the axis, and which is normally it is a curved axis, and curved axis that typically gives the shape of this flow passage. So, steam nozzles are generally curved, and when the nozzle is used for perfect gases, it can be either circular or rectangular. And mainly other difference I have already said that when we use the convergent divergent nozzles, main intention is to generate the thrust, and when you use this curved axis nozzles, main intention is to generate power. Now, we will move on to next topic, that is steam nozzles. Till this point of time, we have been discussing about the theoretical aspects of nozzles, and which mainly deal with the gases. Now, when you talk about steams, same thermodynamic concepts can be used here with a reasonable approximations. For example, when you use the isentropic flow for gases, we use Pv to the power gamma is equal to constant, but when you use this for steam, so gamma is replaced by a parameter k. K is nothing but the polytropic index for the steam. Then rest of the things or rest of the theory remains as it is. So, by replacing gamma with k, we can have a good estimates for critical pressure ratio, critical velocity at the throat and all other cases. Now, when you deal with these steam nozzles, the initial state of the steam can be at superheated state or it can be at saturated state. So, there are two cases, one is dry saturated, other is superheated state. For that, a suitable approximation has been made, for which K was taken as 1.135 for a dry saturated state of steam in the nozzle, and K is equal to 1.3 for superheated state of the steam entering in the nozzles. So, based on that we can simplify all these expressions. We can also find out the critical velocity of the throat. Of course, here another difference we will have to see is that enthalpies, instead of enthalpies we have to use steam tables rather than not as Cp times T, because it will not give a good approximations. And based on that we can recall our TDS equations, then we can find out what is the enthalpy difference between two states. So, these are the some theory which you can apply when to find the state of the thermodynamic states while dealing with the steam nozzles. Now, moving further, for steam nozzles, when you think about the expansion in the nozzles, the another practical phenomena that drops in, which we call as super saturations. Similar term super saturations we also see encountered when you dealing with the steam turbines as well. Of course, for the sake of continuity we will move little bit more what is this state, because this super saturation states is an irreversible phenomena and normally it is called as metastable states. So, what it means is that you recall our molecular diagram, HS diagrams and temperature entropy diagrams. Here we see that steam in its superheated state, that is state 1, expands from the pressure P1 to P2, and this expansion process is in isentropic manner. So, 1 to 2 is the way we say that 1 to 2 is the expansion process which occurs in an isentropic manner. Now, let us see that when it expands, we have since it is a liquid vapor mixtures, we can think of a dome, construct the dome, and while expanding from 1, the steam crosses this dome at point A, which means that we can divide this entire expansion process 1 to 2 as 1 to A and A to 2. So, here also in a molecular diagrams we look the process, we draw the process in this manner. But what it says is that when it reaches almost at the point A, that means when it touches the saturation point at A, the steam is said to be at that condition is said to be metastable. Why? Because it has been seen that although it is a superheated state, but it expands further down the line, that means at point A the condensation is supposed to occur. But unfortunately what happens, since the dynamics of this change is so fast that instantly the fluid does not condense. So, it has to take some finite time, and that finite time after some finite time the condensation starts. So, instantly the condensation does not happen. So, the condition of the steam at that particular state we call this as a metastable state, and the expansion is known as super saturated expansions, and this it can occur within the nozzle or outside the nozzles. Now, let us understand here, I mean if you look at the same figure here again, then what we can see practically is that, so same process 1 to 2, and this A is defined at this saturation point when the steam crosses the saturation point, and we will see that from 2 to R the state at which we can say that the steam is super saturated, which means that if you can draw a particular line at that point R, so we can say P R, we have information, we know this condition P 2, and the same state we can extend this as P 2 is the extension line of this P 2, but at this point we will have actual pressure is P R, and if you see also temperature will be also T R. So, P R and T R is known to us, we will see that P R is less than P 2 and T R is also less than T 2. So, this gives a practical information that steam has undergone the super saturations, and the process from 2 to R is a metastable state or irreversible phenomena, and the actual value of 2 is not as 2, but it to represent it is as R. So, which means that we can define a temperature that will talk about or that will give information about saturation temperature, supersaturation temperatures, and by the parameters which we call as degree of supercooling, that is delta T, which is nothing but the difference between T2 and Tr. Other way of interpreting the supersaturation phenomena is that we can find a parameter xi, which is defined at the ratio of P2 by Pr. We can have two in velocity. One is exit velocity if the stream goes from 1 to 2, other is exit velocity Cr when it goes from 1 to R. So, from this information we can say that your Cr, that means exit velocity at the supersaturation case, will be less than C2. Now, moving further, we can also get the information of enthalpy drop, and we also will get the information about the degree of supersaturation. Then going back to the final curve, that is in the PV, pressure and specific volume plot, it will give the information about the mass flow rate, because for mass flow rate we require the specific volume informations. Now, same phenomena it is being plotted, that when the process the expansion takes place from 1 to 2, and we have two constant pressure lines P1 and P2, and from 1 to 2, while coming to 1 to 2, it interacts this dome at point A. That means, at this point the steam interacts with the saturation point. At this point the steam try to condense or vapor try to condense, but instantly it does not condense at a time or suddenly. So, it takes some finite time to achieve this, to continue this condensation process, and during this process what happens, if the expansion takes place from 1 to 2, so we will have a specific volume V2. Now, if the expansion has to take place from 1 to R, we will have specific volume Vr. So, as you can see, your Vr is less than V2. So, based on that we can apply the isentropic law for the steam, that is from process 1 to A as Pv to the power 1.13 is equal to constant, because we are starting from the superheated steam. Now, from A to R we can use Pv to the power 1.135 is equal to constant. So, from these two informations we can find out two mass flow rates. One is the mass flow rate when the fluid expands from 1 to 2, other is mass flow rate when the fluid or steam expands from 1 to R. So, from this we can find out the mass flow rate of the in a saturated supersaturation phenomena is higher than the mass flow rate that for an equilibrium flow. So, basically why we are discussing this phenomena, because of the fact the concept was not known, but in reality when the mass flow rate was measured, then people tried to understand that why this mass flow rate is supposed to be higher than the mass flow rate in the conventional case or equilibrium flow case. Then after so many theories were developed and the concept of supersaturation was framed. So, what it says is that the experimental evidence from this mass flow rate leads to the discovery of the phenomena of supersaturation in the steam nozzles. So, that means people tried to understand the steam nozzles or steam in a conventional way, but unfortunately when they found that the mass flow rate is typically becomes higher than the equilibrium flow, then try to find out the what is the theory behind it. So, with this we say that the supersaturation phenomena is a very critical aspects for the steam nozzles as well as for the steam turbines. So, with this we conclude the nozzles. Now, we will try to solve some numerical problems for based on our discussions today. So, the first problem talks about a situation when a fluid enters in a converging nozzles and it starts with an initial condition of 7 bar and 100 degree centigrades, and expands isentropically to a space which is maintained at 3.5 bar. So, we do not know the fluid conditions. So, we have to find out what is the mass flow rate per square meter of the exit area of the fluid if the fluid is first case helium and other case is ethane. So, let us understand the physical concept of this. So, we have a converging nozzle. The initial conditions is P1 is 7 bar, T1 is 100 degree centigrade, that means 373 Kelvin, and condition 2, that means space. So, this space is maintained at 3.5 bar. So, you can call this as the back pressure Pb as 3.5 bar. So, let us start this problem for the case 1 when the fluid is helium. When the fluid is helium, we also need to have some the information about the helium gas. So, what information we require? We require its Cp as 5.19 kilojoule per kg Kelvin. We can say helium is a monoatomic gas. So, it is gamma is 1.667. Its R value is characteristic gas constant is 2079 joule per kg Kelvin. So, now recall the expression for critical pressure. So, the expression for critical pressure we can say Pc by P1 is equal to twice by gamma plus 1 by to the power gamma by gamma minus 1. So, by putting these expressions we say it is 2 by 2.667 to the power 1.667 divided by 0.667. So, this ratio is 0.487. So, which means your Pc would be 7 bar into 0.487. This number is 3.4 bar. So, Pc means we say that since it is the minimum area, so at this pressure we have 3.4 bar. Since we say that this Pc is whereas your Pb is 3.5 bar. So, which means your Pb is greater than Pc, which means nozzle is not choked. Or in other words, we say that back pressure does not allow the nozzle to be choked. So, once it is nozzle is not choked, we do not have to recall the expression for choking condition of the nozzle, because once the nozzle is choked, all other flow conditions were governed by the choked parameters. But here the nozzle is not choked, so we have to revisit our isentropic relation to get what is the value of velocity at the exit. So, isentropic relation means we need to find out what is T1 T2. So, T1 by T2 relation we can say P1 by P2 to the power gamma minus 1 by gamma. So, P1 is 7 bar, P2 is 3.5 bar, because 3.5 bar because back space pressure is 3.5 to the power that is 1.667 minus 1 by 1.667. So, this ratio is 1.32, which means T2 would be T1 by 1.32, T1 is already 373 kelvins. So, T2 would be 285.6 Kelvin. So, once we know this T2, so we can find out C2 is square root of twice time H1 minus H2, that is twice Cp times T1 minus T2 square root. So, we know Cp, that is 2 into 5.19, T1 is 373 minus T2 is 285.6 square root. So, C2 is, we can find out 952.5 meter per second. Once we know the C2, we also find out specific volume V2, that is R T2 by P2. R is 2079 into T2 is 285.6, P2 is 3.5 bar, that is 3.5 into 10 to the power 5. So, this specific volume will be 1.69 kg per meter cube. Then mass flow rate m dot is equal to A2 C2 by V2. The question is asked mass flow rate per square meter of area, exit area. So, question is asked what is m dot by A2, that is nothing but C2 by V2. C2 is 952.5 divided by 1.69. So, this is 563.6 kg per second per meter square. So, this is what we get when the gas is helium. So, we understood that for helium gas the nozzle flow condition was not choked. Now, let us see what happens when it is an ethane. Now, second problem, when you say it is ethane, so we have to use its Cp value as 1.88 kilojoule per kg Kelvin, its gamma is equal to 1.172 and R is equal to 277.1 joule per kg Kelvin. So, first check that we need to know is that what is critical pressure. Pc by P1, that is twice by gamma plus 1 divided by gamma minus 1. By putting this ratio, we say twice by 1.172 plus 1 to the power 1.172 divided by 0.172, that is 0.57, which means what is Pc would be, P1 is 7 bar. So, Pc would be 0.57 into 7, that is 3.99 bar. Now, since we say Pb is less than Pc, that is 3.5 bar is less than Pc, which means nozzle is choked. So, once the nozzle is choked, we have to use the choking relation. That is Tc by T1 is equal to twice by gamma plus 1, that is equal to 0.92. So, from this we get Tc as 0.92 into 373 is your T1. So, 340. So, we say your C2 would be 334 meter per second, and that C2 is square root of gamma R Tc. So, Tc we have 343.5 Kelvin and C2 we get this. Now, once you have C2, then we can find out what is Vc, that is R Tc by Pc. So, R is 277.1, Tc is 343.5 divided by Pc is known, that is 3.99 into 10 to the power 5. So, this is 0.2385 meter cube per kg. So, then we have m dot is equal to A2 C2 by V2, which means our main intention is to find out what is m dot by A2. So, Tc is 343.5 Kelvin, C2 or Cc is equal to square root of gamma r Tc, that is 1.172 into r is 277.1 into 345.5 square root. So, we get Cc is equal to 334 meter per second. Once you have Cc, then specific volume Vc is equal to R Tc by Pc. So, R is 277.1, Tc is 343.5, Pc is 3.99 into 10 to the power 5. So, this number is 2385.2385 meter cube per kg. So, we have Vc, then we can find out what is m dot is equal to A2 C2 by V2. So, m dot by A2 would be C2 by V2. So, C2 here is Cc, that is 334, V2 would be 0.2385. So, m dot by A2 is 14 is equal to 1413 kg per second by meter square. So, when the nozzle is choked for ethane gas, we find the mass flow rate per square meter of the exit area is 1413 kg per second per meter square. So, in the last problem we talk about a steam nozzle problem, which says that in a steam nozzle the flow expands from in a convergent divergent nozzle from a condition which is 10 bar dry saturated and it expands to a locations where it is atmospheric, which is 1 bar. So, we need to find out the critical pressure and throat area. So, this is your throat area AC, and if you try to plot it in a temperature entropy diagram, so initially the steam is at superheated state, point 1 can be located at 10 bar, point 1 is can be located at the dome, that is 10 bar dry saturated, and it expands to a condition C, and at this condition is nothing but your critical conditions. So, for that we have to recall the expressions for Pc by P1, that is twice by k plus 1 to the power k by k minus 1. So, and since it is dry saturated, we can take k as 1.135. So, by putting this we say it is 2 by 2.135 to the power 1.135 divided by 0.135. So, we can say what is Pc by P1 ratio, that number we say 0.577. So, we can find out what is critical pressure is initially it is 10 bar. So, it is 5.77 bar. So, basically steam expands from 10 bar to a critical pressure at throat, typically it will happen at the throat to 10 bar. And once we know these critical pressures, then we can find out the other conditions. Other conditions we require the throat area. For to calculate this throat area, we require also mass flow rate. So, from this we have to say that state 1, so we have to refer steam table. State 1 we say P1 10 bar dry saturated, which means we can find out its enthalpy S1 as 6.5863 kilojoule per kg Kelvin, then H1 as 2778.1 kilojoule per kg, and state 2 critical condition or state C we can find out HC, that is at 5.77 bar, and it is in the saturated liquid vapor or it is liquid vapor regions. So, for that we have to know what is this dry next fraction XC, that number we can find out 962, and HC we can find out as 2675 kilojoule per kg Kelvin. I am omitting some of the steps to calculate this because it is a constant entropy process. Maintaining entropy as same as HC, we can find out what is XC, and we know we can find out what is enthalpy at C, and of course, we can find out specific volume 0.316 meter cube per kg. So, once you have these informations, then you can find out what is Cc, that is square root of twice time H1 minus Hc, twice into 1000 into 2778.1 minus 2675, that is equal to Cc is equal to 454 meter per second. Then we have m dot is equal to A2 C2 by V2. Our expression is what is asked is what is the throat area per unit mass flow rate, that is A2 by m dot is equal to V2 by C2 or Vc by Cc. So, A2 by m dot would be Vc is 0.316, Cc is 454. So, this is A2 by m dot would be this much meter square, and if you convert it to mm square, it will be 0.316 into 454 into 10 to the power 6. So, this is approximately 696 millimeter square per kg mass flow rate. So, we got this critical pressure Pc, we also find out the throat area per unit mass flow rate 696 millimeter square. So, with this I conclude. Thank you for your attention.